In one of our previous videos, we were able to show that a specific vector w was a linear combination of these three vectors v1 through v3. We're going to tweak that question a little bit and generalize it to this: is any vector w a linear combination of the vectors v1 through v3? It's important to keep in mind that the vector space that we're working with here, V, is none other than R3. And so this question can really be rephrased as, is every vector in 3 space going to be able to be expressed as a linear combination of v1, v2, and v3? So in other words, do these 3 vectors generate R3? We already know that I, j, and k do, but there might be, a different set of 3 vectors that, do the same job. And we're going to put these 3 vectors to the test. Now, we do have to be a little more general here. So I'm going to make a note, maybe over to the right. We're not picking a specific vector w, so we'll have to work with generic components. I would like those components to be labeled as w1 through w3. And we're trying to answer this question: is w going to always be expressed as k1 v1 plus k2 v2 plus k3 v3, regardless of what values we pick for w sub 1 to w sub 3. Now, if we try to approach this the same way we did the very first problem of this section, I hinted at us putting it in augmented matrix format. And the augmented matrix format, using all this information, would be as follows. The first column, 2, 1, and 4, those are the components of v1. Then 1, negative 1, 3, and then 3, 2, and 5. Now, the components of the vector w are not specific values, they're generic. And so, if you try to RREF that, you might say just that. F that. So, this is really not the approach that we want to take for a problem like this. Instead, what you're going to want to do is rewrite this in matrix equation format. So how do I want to say this? Let's say use this instead, or use instead. Now, the matrix equation format, I'll write as AX equals W. And I'll bring these matrices in. A is a coefficient matrix that's going to be built out of the components of V1 through V3. And actually, we have the coefficient matrix A hidden within our augmented matrix format. So this time A, let's write A as a 3 by 3. First column 2, 1, and 4. Second 1, negative 1, and 3. And then 3, 2, and 5. As for the vector X, that's going to be a column vector corresponding to what we're trying to solve for. And what we're trying to solve for here are the scalars k1, k2, and k3. Alright, that's what we're trying to solve for when we're expressing a vector as a linear combo. So k1, k2, and k3. And the constant matrix on the right-hand side would be those specific values of w1, w2, and w3, which we don't have specific values of those. But that's okay. What this really all boils down to is whether or not this matrix equation can always be solved. And what we look at to see whether or not that's the case would be the determinant of the coefficient matrix A. Now, if the determinant is non-zero, then we will always have a way of finding k1, k2, and k3. Whereas if it is 0, there are going to be certain vectors in the space that cannot be expressed as linear combos of v1, v2, and v3. So that's kind of the criterion. Look at the coefficient matrix A associated with a linear system that could be formed here, and consider the determinant of the coefficient matrix A. If this determinant is non-zero, then the answer would be a resounding yes, because we would always be able to find the scalars k1 through k3 no matter what values you pick for w1, w2, and w3. So without further ado, I will let you know that the determinant of this matrix I got as 2, which obviously does not equal 0. And what this implies is that, yes, any vector w can be expressed as a linear combo of v1, v2, and v3. Alright, so as a matter of answering the question posed, yes. And again, the rationale, which I'll include, is this. The matrix equation AX equals W will always have a solution. And what this means is that no matter the values W1, W2, and W3, we will always be able to find, that's kind of a derpy 2, I'll leave it as is though, it needs some loving. We'll always be able to find K1, K2, and K3. So that's the rationale. As for the technique, it's really not all that difficult. You form the matrix equation and just evaluate the determinant of the coefficient matrix A. Now, since we've identified that any vector in R3 can be expressed as the vectors v1, v2, and v3, we can represent R3 as the span of something other than I, j, and k. Specifically, R3 can now be expressed as the span of our vectors v1, v2, and v3 from this current problem. Alright, so that's it for this video. As always, let me know if you have questions. Otherwise, I'll see you in the next one, and thank you so much for watching.